But the effects which are produced by currents which rise instantly to high values, as in a disruptive discharge, are entirely different from those produced by dynamo currents which rise and fall harmonically. So, for instance, there might be in a given case a number of makes and breaks at dd equal to just twice the frequency of the dynamo, or in other words, there may be the same number of fundamental oscillations as would be produced without the discharge gap, and there might even not be any quicker superimposed vibration, yet the differences of potential at the various points of the circuit, the impedance, and other phenomena dependent upon the rate of change will bear no similarity in the two cases. Thus, when working with currents discharging disruptively, the element chiefly to be considered is not the frequency, as a student might be apt to believe, but the rate of change per unit of time. With low frequencies, in a certain measure, the same effects may be obtained as with high frequencies, provided the rate of change is sufficiently great. So if a low-frequency current is raised to a potential of, say, 75,000 volts, and the high-tension current passed through a series of high-resistance lamp filaments, the importance of the rarefied gas surrounding the filament is clearly noted, as will be seen later. Or, if a low-frequency current of several thousand amperes is passed through a metal bar, striking phenomena of impedance are observed, just as with currents of high frequencies. But it is, of course, evident that with low-frequency currents it is impossible to obtain such rates of change per unit of time as with high frequencies, hence the effects produced by the latter are much more prominent. It is deemed advisable to make the preceding remarks, inasmuch as many more recently described effects have been unwittingly identified with high frequencies. Frequency alone in reality does not mean anything, except when an undisturbed harmonic oscillation is considered. In the branch 3b, a similar disposition to that in 1b is illustrated, with the difference that the currents discharging through the gap dd are used to induce currents in the secondary S of a transformer T. In such case, the secondary should be provided with an adjustable condenser for the purpose of tuning it to the primary. 2b illustrates a plan of alternate current high-frequency conversion which is most frequently used, and which is found to be most convenient. This plan has been dwelt upon in detail on previous occasions, and need not be described here. Some of these results were obtained by the use of a high-frequency alternator. A description of such machines will be found in my original paper before the American Institute of Electrical Engineers, and in periodicals of that period, notably in the Electrical Engineer of March 18, 1891. I will now proceed with the experiments.